Let's talk about multiple object systems, and in particular, what happens when parts of that system, quote, interact with each other. Here's an object I'm labeling object 1, and it has an initial velocity indicated by that vector v1 initial. And it's moving right toward a stationary object 2 that you see there. So during this interaction, well, what do we really mean by interaction? I mean, I guess we're saying here when they physically they'll bump into each other, if they actually physically touch each other. They might not do that. What if there are things that can get near each other and don't touch each other, but still are able to interact? Like what if this one's a positively charged something, and so is this one? Those two kinds of things will get near each other, and they most likely won't touch each other, but they still interact. And so what do we really mean by interact? What we mean is, and that's code word for apply forces to each other. That's what we mean. That's what force is. Force is an interaction between two objects. So during this interaction, let's talk about the forces that these objects exert on each other. Well, we can represent them with vectors. And we can say that there's a force exerted by 2 on 1. So when I say I'm going by on. And there's a force by 1 on 2. Well, what do you know about those forces? These are two objects exerting forces on each other. And what we know by now, I hope, is that these two forces are partners in a force pair. Those two forces are equal and opposite. All right? They're the same kind of force. What kind? I don't know. A normal force? Maybe it's what we call an electrostatic force because they're two charges. Maybe there's somehow we have magnets on each thing aligned in the right way, and there's a magnetic force that each one applies to the other. Regardless, those two forces are the same size and point in opposite directions. And if we look at how those forces vary as a function of time during the interaction, well, the application of force is not something that can happen instantaneously. It has to take time. And so while we might represent F by 2 on 1, like, all right, they haven't interacted yet. Okay, they bump into each other, and then they separate, and then they're not interacting anymore. All right, maybe somehow the plot of F2 on 1 as a function of time looks like that, where there's, some F21 max. And maybe there's some average value of this that we could find via some calculus process, but who cares? Well, the question is, what does F12 look like, the force by 1 on 2? Well, guess what? It's the same. It's always the same, except, hang on, stupid, undo. All right, here's what we want to do. We want to clone. Give me this, and then flip it. Vertical. Up, down. And then I want it to turn red. Good. So look, there's the force by 1 on 2. It's the same exact size force at any and every instant, and it's in the opposite direction. Right? Take any instant. Here's an instant in time right now. Right? Well, there's the value of that force. Here's the value of this force. These forces have the same magnitude. They're just in opposite directions. Okay? And so, that hopefully isn't anything real new. The idea that maybe a force versus time profile can look like this, maybe that's new. But, big deal is forces can't only be applied for an instant. The application of force takes time. It occurs over some measurable time interval. Whether it's big or small, it's something. All right, so what does that mean? What does that mean about How can we further develop this when we talk about objects interacting? Well, let's take these two objects, M1 and M2. Well, here's what we said. At any instant, the force that one exerts on the other is equal and opposite to the other force that the other exerts on the first. And these times are the same. And you might notice that overall, if we took the whole area of this shape and the whole area of this shape, they're the same. All right? And so what we say really, or what we can say is, for each object, well, there's like the force on 2 by 1. I'm not sure how my notation was before. The force by 2 on 1. Well, we said that's equal and opposite to the force by 1 on 2. Right? And maybe we write those as deltas. The time that these two forces are applied are equal. And so what we can say is F21 times that t is equal and opposite to F12 times that time. Same amount of time. The products are the same. The areas are the same, right? This product, if we say, you know, maybe like the average force, those products are the same. All right, now I'm actually going to change a little bit here and make sure we're saying that these forces are vectors, and that's why we can have that negative in there. All right, because we mean equal and we mean opposite direction. All right, now what do we know about force? Well, this force, this is a by 2 on 1, so this means that this force results in an acceleration of object 1. And I'm going to leave this delta t, and I'm going to say this is negative. Whoops. Well, this force is going to account for mass 2's acceleration during that amount of time. Now, these accelerations are vectors. All right. Now, these accelerations can be written as, m1 delta v1, where delta v is a vector. Negative m2 delta v2. Right, here's that t. Delta v2 is a vector. And now I'm going to get rid of these amounts of time. And what we're left with is this statement. M1 delta V1 is negative M2 delta V2. And this by itself, you know, maybe doesn't look too wildly interesting, but it says, I mean, for a lot of scientist types, this sort of points to an important type of statement. This type of statement where one thing is equal and opposite to another, right? There are, this says that when objects interact, they experience equal and opposite m delta v, product of m and delta v. So the product of m and delta v, for one thing, is equal to the product of m and delta v for another thing. Or they have equal and opposite, that's one way of saying it, they have equal and opposite changes in the product of mv. Vector. M delta v is the change in mv. Agree? So here's this thing where, you know, the product of two quantities apparently shows us something interesting, or can be involved in an interesting phenomenon. In this case, when two objects interact, if we look at the product of each object's m and v, those are going to change by the same amount in the opposite um, direction, by which I mean either to the left and right, or bigger and smaller, or increase and decrease. All right, so we get those changes. Well, and so this is therefore defined. If this is something of interest in a very common situation like two objects interacting, if this is something that we see shows up, then we'll name it. All right, and that is called momentum. By definition, an object's momentum that looks like a P, but it's usually a Greek lowercase rho. It's like a lowercase p, but it's fancier. Sure. By definition, momentum is the product of an object's mass and velocity. All right? That's it. That's the definition of momentum. There's not like, you know, like, that's just it. Just a definition. Similar to how we say velocity is defined to be the rate of change of position. All right? So, if momentum is m times v, then m times delta v is a change in mv, a change in momentum. When objects interact, they experience equal and opposite changes in momentum. And then we name this. Change in momentum, delta momentum, is what we call impulse. So J equals, well, let's see, change in momentum, impulse, yeah, sure, impulse, by definition, change in momentum, by definition, is change in momentum. But remember, where did we get these m delta v statements? They came from here. So we said, okay, f delta t I can turn into ma delta t, I can turn into m delta v over t, t equals m delta v. So m delta v is also f delta t. All of these things are ways of expressing, calculating impulse, a change in momentum. What's momentum? It's by definition the product of mass and velocity. Who cares about momentum? Well, we care because we can see that during interactions, this product of m and v, or at least how it changes, is something of interest, or shows us something interesting. We get these equal and opposite changes in that product during the interaction. Okay, so when objects interact, well, we now have a whole, right, when objects interact, when they apply forces to each other, we now have a whole bunch of statements that we can say are true. One, there's equal changes in m delta v. Or sorry, there's equal and opposite, yeah, m delta v's. There's equal and opposite changes in mv. There's equal and opposite changes in momentum. There are equal and opposite, well, 4, there are equal and opposite, there are equal and opposite impulses. Impulses. Okay? So what does that mean? Or, you know, what else might this show us that's interesting? Well, let's not go there quite yet. Let's go here. And let me restart from here. M1 delta V1 is negative M2 delta V2. That doesn't come out of nowhere. That's this, well, that's this. I'm building from there. I mean, this already sort of tells us something about momentum. If during an interaction, two things, momentums can change, but those changes are equal and opposite, that tells you something about momentum if you're willing to think about it enough. but we can explicitly show what that means if we expand this a little bit and write it like this. Well, delta V1, V1 final minus V1 initial. Agreed? Negative M2 delta V2, V2 final minus V2 initial. Let's distribute because we feel like M1 V1 final minus M2 V2 final equals, all right, negative M2 V2 final plus M2 V2 initial. Oh, I put up, what? Sorry, this is totally wrong over there. M1 minus M1 V1 initial. Thank you. Now that's normal algebra. Okay, who cares, except maybe, now notice, here I'm talking about what happens to each object. What happens to object 1? What happens to object 2? We can change that and say, instead of comparing one object to the other, let's compare now to now. Initial to final. So if I put all the initials on one side, it's going to, notice, I would add this term to both sides, but I don't want to move it over here. So I'm going to put all the initials on one side. M1 V1 initial and M2 V2 initial. Right? If we get all the initials on the right, they're all positive, but I'm going to put them on the left because I feel like it. And then if I move this guy over here, I would add it, so that means we're adding the finals, and then we get M1 V1 final plus M2 V2 final. And so this starts to show us something, or be a more clear picture of what's true about the product MV. Oh wait, the product of MV, well, that's momentum. This is the first one's initial momentum, M1 with its initial speed. Sorry, velocity, not speed, don't say that. Well, that's P1. And P, if I didn't say it before, is a vector. I did say it before. And look, here's the second one's initial momentum. And then here's the first one's final momentum. And here's the second one's final momentum. And guess what? We've been talking about a system of two objects, right? We have two objects, what do you call it, interacting. So, you know what this is? It's all of them. It's all of them added up. It's the sum of all the initial momenta is the sum of all the final momenta, is equal, has to be equal to the sum of all the final momenta. And that says that this is also a very, for us in the physics world, something very, it tells us something very profound. It says that initially and after that, there's the same total amount of something. So this says that before and after any interaction, there exists the same total system momentum. See, that sort of sounds like something we talked about with, like, I don't know, like a pendulum or like a roller coaster sort of thing, except we didn't say momentum, we said energy. And what does that mean about energy? Well, it means that energy is conserved. Well, what does this statement mean about momentum? It means that before and after any interaction, or even during any interaction, momentum is conserved. All right, now a minute ago you heard me say, this says something very interesting about momentum if you're willing to think about it. Right? What does that say? That says that during an interaction, one object's momentum changes by the same amount that the other one's does, but with a different sign. And so it says, okay, maybe this object gains some momentum. Well, then that object must lose that momentum. Well, guess what? That's the same exact thing as saying if one gained some and that came from the loss from the other one, that means there's the same total amount all the time. And it means that momentum is conserved. All right, so a hugely powerful statement about what happens in the right conditions, of course, right? If we're neglecting, what we call non-conservative forces, like that there's lots of friction between, that there are forces other than just the two forces that the objects are exerting on each other, that's going to make for some perhaps less perfect situations. But as we typically do, we'll neglect stuff like that. All right, so let's try to apply. Let's apply to a case like this. Here are two objects, and we're going to say that they are limited in this case to moving in one dimension. All right, all they can do is move on this line. All right, and this mass m, we're going to say, has an initial velocity v initial like that, and mass 3m has an initial velocity of 0. Right, they're going to what we call hit and stick, literally hit and stick together. And so afterwards, what's going to happen? What's going to happen is this and this are going to stick together, and they're going to move with some common final velocity. This is that dotted line there, not this one. That dotted line that I just drew is my before and after demarcation. All right, so before the interaction, here comes mass m moving with speed v initial towards mass 3m. Afterwards, the two are moving at some final velocity that we'd like to express. Well, there's a couple of ways to do it, but the most standard way is to say, all right, let's apply the fact that momentum is conserved. And then we say, I usually jump right to here. Here's the first one's initial momentum. Here's the second one's initial momentum. Here's the first one's final. Here's the second one's final. And then we get to say things like, all right, what do we know? What might we get rid of? Oh, look, yes, yes, yes. Bye-bye. All right, now we can say, well, in the end, these things move with the same common speed. So this actually is going to turn into m1 v1 initial equals, well, watch this. If it's m1, if I say that v1 final and v2 final are the same v final, then what we can do is actually write this as v final, m2 v final, and then we can factor out that v final. Or it sort of makes sense when you say it like this. It's the two objects stuck together moving at a constant or a common final velocity. Now, what are our m's? Ours are m and 3m, right? If we want an expression for our v final, it's going to be m1 v1 initial divided by the sum of our two masses. Or, well, let's see, this is, for us, m, v1 initial, divided by m plus 3m. Well, our final system velocity is v over 4. Sort of makes sense, and here's why. In the beginning, we had one unit of mass moving at speed v. I'm supposed to have initial there, right? The total system momentum is mv, right? This one doesn't have momentum. Speed is 0. In the end, the total system momentum still better be mv. Well, it is, because now we have 4 units of mass moving at that speed. And so V over 4 times 4m, yeah, is mv, just like it was in the beginning. All right, we can also look at impulses of either object, changes in momentum of either object. So delta P1 is m delta V1 is m1, I guess. Now V1 final is V over 4, and V1 initial was just V initial. So that's negative 3 3m over 4. 3mv over 4. Yes, 3mv over 4. Agreed? This is negative 3/4 V initial. There's our V initial. Delta P2 is, let's see, 3m. Well, how about this? It's m2. Delta V2. What's m2? Well, it's 3m. V2 final is V over 4. V2 initial was 0. Well, that's 3mv over 4. And notice, yes, those are, as they have to be, equal and opposite. Their changes in momentum are equal and opposite. Okay? So, I mean, you know, as a cruncher of numbers and a smasher of equations, that's the form of the equation that you'll use most typically. All right. The development of that and what it means is, to me, more important. And so that comes from, you know, the idea that when objects interact, they apply equal and opposite forces to each other for the same amount of time. That allows us to develop this phrase and idea of change in mv, and then the definition, therefore, of, okay, what do you want to call this thing mv that's changing? Let's call it momentum. And, you know, if change in mv seems to be, you know, a pretty interesting phenomenon, let's name that. We call it impulse, J. You know, what's impulse equal to? Here's the definition. Here's 2 ways to find it. All right, and then how do we use this? How can we use this as a predictive tool, perhaps? Well, we can, you know, use this in one case to come up with a pretty bold statement about momentum, right? And that's that during any interaction between 2 objects, or really any number of objects, the total system momentum has to be constant. There has to be a conserved total amount of momentum. And then we can, you know, kind of get to the nitty-gritty and use this as a problem-solving tool that looks like a big ugly formula, but, you know, I guess deal with it. There it is. You can use it to solve lots of questions. Here's one simple one, but lots of questions about interactions. All right, big deal is, notice, V and P and J are vectors. So sine, there's got to be some convention that you choose and stick to that says, okay, something moving left and something moving right can't have the same momentum. Their momenta are not the same. All right, one might be, an object moving west might have what you decide to call a positive momentum. An object moving east, therefore, would have to have what you'd call a negative momentum. Okay? My dudes, here's what I want you to try. All right? You're going to try this. We have a mass moving at speed v initially. To the right. Bumps into another 3m mass that's not moving. My dude here is going to rebound with a velocity v over 4, but to the left. to the left, I remind you. And the question is, what is this thing's final velocity? Okay. The answer that you're going to get is v over 2 to the right. Is that true? Let me just make sure. Yeah, I think it's true. No, it's not v over 2 to the right at all. I think it's 5/12 v. Whew. Yeah, I think it's 5v over 12 to the right. Yeah, that's what it is. Okay? So, yeah, I think see if you can run through this solution and get that to prove itself out. Okay? And, gee, how do I do this problem? Well, here's how you do it. Apply conservation of momentum. All right, be careful with direction. This is not a hit and stick, right? This one here is a hit and bounce. This is not a hit and stick, so you do not say that there are two things moving with a common final velocity. You do not say that. All right? But you isolate the thing you want to isolate. Okay? Good luck. See you soon.